Hi everyone. So today we're going to talk about density and pressure when it comes to fluids. So kind of an introduction. I've tried to kind of consolidate my PowerPoint to be as short as I can. So let's move on. Okay. All right. So first thing, let's do a warm-up question here. So I'll ask you, what's the difference between the study of statics and dynamics? So try to think back what you know what those means and what the difference is. And what do you think of when you hear the words fluid? So take a couple moments here and reflect on these and write your answer. All right, so hopefully you realize that the difference between statics and dynamics, statics means still and dynamics means dealing with forces. So typically we're dealing with things accelerating. So when it comes to fluids, and I'll define fluids in a moment, but we'll be discussing both those things. So what happens, how fluids behave when they're still, and how do fluids behave when they're accelerating or dealing with forces. All right. And what do you think of when you hear the word fluid, right? So maybe you said, oh, water. But maybe you also thought air, and both these things are correct, right? So this is because fluid is a substance that flows, all right? So this means that both gases and liquids are fluids, all right? So the difference between a gas and a liquid in the sense of fluids is that gas can be compressed where liquids are incompressible. At least the liquids we're going to be dealing with, we're going to assume they're incompressible, right? Meaning you can't change their density. Where gas, you can change the density of them. So I use this word density. What does density mean? So density, so in particular when I say density, what I mean, I inherently mean mass density. Right? So if I say density, that's what I mean. So mass density, we're going to use the symbol rho to define it. All right. So you might be thinking, oh, in middle school we used D to symbolize density. Not anymore. We're using Greek letters. All right. So the Greek letter rho. There are different types of densities. We're actually particularly implying volume density. We can also, well, we're not going to be dealing with this, but in college you might deal with area density or linear density, all right? So that's just kind of a fun fact. But volume density is the amount of stuff per unit volume. So you're dealing with that mass divided by volume, kind of long story short. So units here, we're dealing with mass in kilograms, volume, meters cubed, so we end up with kilograms per meter cubed for our SI units for volume, or excuse me, for density. Now, what's important about density is that it's an intrinsic property of the substance, right? So the mass density is based on the structure of the atoms and molecules kind of interacting with each other. So a substance is going to, all objects made up of the same substance are going to have that same mass density, no matter what their size is. So some common densities, I found a table here online. I just wanted to have you be aware for it. The table here has things other than just fluids, but I thought this might be a good reference for you. You can just Google various densities online. Most importantly, the density we're going to be dealing with most often is going to be the density of water, just regular water. So STP, standard temperature and pressure. And that's going to be, it's actually a pretty easy number to remember. It's 1,000 kilograms per meter cube. All right, so that's the density of water. You don't need to memorize this on the AP exam. They give you any densities that you might need. It's not on the reference sheet, but it's not something you have to memorize. But density of water is something you just might happen to memorize because it's easy to remember. You might need these densities for the homework. So maybe in the homework you might be dealing with something floating in, let's say, mercury, all right, or the fluid you're looking at is a mercury thermometer, perhaps. So you might need to know the density of mercury or look that up, and here you can see on the table that it's 13.6 times 10 to the third power kilogram per meter cubed. All right. So take a moment here and answer this question. So let's suppose we have a piece of glass and it's broken up into I say 3 pieces here. It's 2 pieces. Sorry about that. But I want you to rank in order from largest to smallest the densities of these 3 pieces. All right. So rank the density of the original glass into its 2 broken pieces. All right, so hopefully you answered that the densities are the same, right? So glass, even though it's broken up into two smaller volumes, or technically areas here, but anyway, two smaller pieces, right? Well, the mass is also broken up, so to speak, in the same ratio. So the density doesn't change. The glass, the inherent structure of the glass material itself hasn't changed its density. So all these densities here are equal. All right, so let's move on and talk about pressure. Right, you probably intrinsically know what kind of pressure is. When you think of pressure, right, so maybe you're pushing your hand against the table. So pressure, you're thinking, oh, it has something to do with force, right? And that's true. Just be careful though, because pressure is not equal to force, right? It's actually going to be equal to force divided by area, right? So pressure is the force applied to a specific area, and that's what that area is, A. Okay. So we're going to be using pressure quite a lot. This is a simple definition. This is not our only definition of pressure. All right. So this definition is useful if we know how much force is being applied in a certain area. All right. So the units here, the SI units, are known as pascals. All right. How a pascal is defined? Well, looking at our formula, we're dealing with force divided by area. So that's newtons divided by meters squared. So 1 pascal is 1 newton per meter squared. All right. So pascal, we abbreviate that as PA. All right. And something that's important to mention, and honestly, this is like a whole bullet point that AP wants you to know, so I do want to make sure I don't forget to mention this. Right. When you're dealing with pressure, in particular with a fluid, the pressure of a fluid is not just dealing with the fluid interacting with the container, but it's also a property of the fluid itself. So let's just say we're dealing with air, right? Air is made up of air molecules. We'll leave it at that. We'll say air molecules. When we have these air molecules, and the pressure exists within the fluid itself, so these molecules bumping into each other, exerting forces on each other, right? So there's intrinsic the pressure is inside that fluid, whether or not that those air molecules are bouncing into the container that it's in. All right, so it's due to both those things. All right, so let's think about how pressure can be applied to fluids and what can we learn from this, all right? So I want you to look at this picture on the right. So what's going on here is we have a container of, let's say, water, all right? And this water, if you look at this container, the top is open, so that means this container is open to the atmosphere or the surrounding, in this case, air around it. And there are 4 holes punched in this container. Let's assume that each of these holes is equal size, so equal area. And you see here that then the water shoots out of these punctures. All right, so looking at this diagram, we see here that these streams of water don't all end in the same spot. All right, so that's pretty interesting. So I'll ask you, why does the water flow out of these holes in the container? All right, so kind of a hint here. Why does the definition of pressure apply to this situation? So what's going on here is that the pressure inside the container is larger than the pressure outside the container. All right, we can see this because at, let's say, the top hole, in that exact spot, we've got force. So we're dealing with pressure, right? Pressure is force over area. All right. As we know from forces, if we have a net force, we're going to have an acceleration. We see here that that our water is flowing to the right there, out of the hole. So therefore, the force on the left has to be larger than the force on the right in order for that to happen. It's because the water is accelerating out. So because of this, in the areas we're dealing with, the area being the hole is the same for just immediately inside the container, immediately outside the container. We therefore have to have a larger pressure inside the container compared to outside. Right? So you really want to make sure your definition does kind of go into that much detail to explain why this is happening. Next question here is the pressure of the water in the container constant? and why or why not. All right, so look at these 4 holes and think about whether the pressure is going to be constant throughout the container of water. All right, so the pressure here is not constant, right? In fact, we can analyze this and see that the pressure is increasing as we go lower in the container of water. All right, we can see this because we're looking at those punctures. Well, we see that the bottommost hole has the water shooting the furthest. This means that the water has the largest horizontal acceleration at that point. So therefore, it must have the largest force at that bottommost point, and therefore the largest pressure. All right, so we can see here that as compared to, let's say, that top surface of the water, the pressure is increasing as we get lower and lower in depth in the water. So why is this happening, right? So we'll talk about pressure in liquids in particular, right? So I am talking about liquids, not fluids in general, so not gases. So when it comes to liquids, it's actually the force of gravity, so the weight of the liquid itself, that's responsible for the pressure in a liquid, all right? So you can kind of actually feel that, like if you imagine like you're swimming in a swimming pool or the sea or anything, as you kind of dive down deeper, you can literally feel that pressure. It feels heavier on top of you, and that's literally just because kind of, right above you, you have more volume, more mass of liquid, so therefore there's more weight. All right, so that's literally what's going on. But it's not just the liquid above it, it's actually whatever's above that as well. So if you have some container of a liquid, it's also whatever's going on above the surface of that liquid that matters as well, right? So that could be another liquid, or it could be the atmosphere. So we'll kind of get more into that a little bit later. But basically, just kind of imagine vertically upward on whatever you're analyzing. Analyzing that forever, and whatever is above that is important too. It adds to the weight, so it adds to the pressure. So this is useful. Okay, 3 minutes, cool. Because we have a formula for pressure. Right? Usually I'd go into deriving this formula with you, but we're going to move on from that. So this is known as the hydrostatic or absolute pressure formula. All right, so a hydrostatic, right? So hydro, you think water, right? But we're dealing with liquid here. Static, still. So this formula is only valid for fluids, and actually it's fluids that are still. And actually also mentioned with constant density. But anyway, so what this pressure does is it says that the pressure at a certain depth in a fluid is equal to the pressure at the surface of that fluid plus rho gh, being the density of the fluid, times the acceleration due to gravity, times whatever depth you're dealing with. So that's the depth from the surface. Your formula sheet uses h for height, but I'd rather think of it as depth. All right. So we'll look at, when we're problem solving here, drawing a sketch will help us with that. Now, if we have our liquid open up to the air, then this P naught term, the pressure at the surface of the liquid, that's going to be atmospheric pressure, which is 1.013 times 10 to the 5th newtons per meter squared. Right? Write that down. That's important. You're going to be using that a lot. You can also write this as P atmosphere. But if our fluid is not open to the air and open to, let's say, another fluid, you're going to have to maybe compute what the pressure at the surface of that liquid is.